Hello students, it's Mr. Sagers back with another video for Earth and Space Science. Today's topic is plate tectonics. By the end of this video, you should be able to construct an explanation for how plate tectonics results in different patterns on the Earth's surface. Let's get to it. Plate tectonics is a relatively modern theory, put forth only within the last century. Simply stated, the theory of plate tectonics suggests that Earth's crust is not uniform around the planet. Rather, it is broken into pieces or plates that fit together much like a jigsaw puzzle. Furthermore, these plates are not stationary but slowly move about the planet. This movement can explain phenomena such as earthquakes, volcanism, and even the formation of entire mountain ranges. Scientists have identified 7 large tectonic plates as well as several smaller ones that make up the Earth's crust. Many of these tectonic plates have been named for the geographic region and/or continent that they comprise. Thus we see names such as the North American plate, the Pacific plate, and the African plate. Some of the smaller plates may have names that are unfamiliar to you. See if you can find the Scotia plate. What about the Nazca plate? Or the tiny Juan de Fuca plate? If needed, you should take a moment to pause this video and become familiar with the names and locations of each of Earth's major tectonic plates. Bear in mind that Earth's tectonic plates may be comprised of more than one type of crust. Recall that in a prior video we learned that the Earth's crust is made of 2 main types of igneous rock, granite and basalt. Remember that continental crust is made primarily of granite, which has a density of about 2.75 grams per cubic centimeter. Oceanic crust, made mostly of basalt, is denser at about 3 grams per cubic centimeter. These 2 types of crust, continental and oceanic, make up Earth's tectonic plates in varying proportions. Continental crust is, on average, thicker than oceanic crust and may extend up to 70 kilometers below the Earth's surface. Oceanic crust, conversely, may only be about 10 kilometers deep at its thickest. Whether oceanic or continental, the Earth's crust is often referred to as the lithosphere and is distinguished from the plastic upper mantle by its rigid nature. If you are like many of the scientists of the early 20th century, you may wonder, what force could possibly be big enough to move an entire continent, let alone the plate of which that continent is a part? Remember that in a previous lesson we studied Earth's interior. Energy from the Earth's core is responsible for the motion of Earth's tectonic plates. As that energy radiates outward, it heats the mantle and creates convection currents. This causes heat and matter to slowly rise through the mantle in some areas, while in other areas, cooled material sinks back downward. These currents slowly drag the rigid plates of the lithosphere across the upper mantle. This movement occurs relatively slowly. In fact, the fastest moving plate today, thought to be the Nazca plate, only moves at a rate of about 16 centimeters per year. That's just as fast as your hair grows. Geologists have long noted a preponderance of certain geologic activity in some areas and not at others. For example, why are earthquakes so common in places like Chile or Japan? What created the many volcanoes known as the Ring of Fire around the Pacific Ocean? Why do mountain ranges form where they do? These questions and many others can be answered by examining the way that tectonic plates behave at their boundaries. Specifically, we will explore 3 types of boundaries: divergent boundaries, convergent boundaries, and transform boundaries. Divergence is a process that results when 2 tectonic plates move away from each other. This can occur when 2 adjacent plates are situated atop convection currents that draw the plates in opposing directions. When plate divergence occurs between 2 plates made of oceanic crust, the divergent boundary results in the formation of a mid-ocean ridge. Superheated material from the mantle flows upward to fill the gap between the spreading plates. This results in the formation of new ocean crust as well as the presence of underwater volcanoes. Older crust is located further away from the mid-ocean ridge as the newer crust flows in to take its place and push it away from the spreading center. A prominent example of this type of divergent boundary can be found in the Atlantic Ocean between the North American and Eurasian tectonic plates. Submarines during World War II first detected the mid-ocean ridge by accident as they used sonar to map the ocean floor. Further investigation revealed an underwater mountain chain spanning the distance from Iceland down through the southern waters of the Atlantic near Antarctica. The spreading of the tectonic plates is responsible for the divergent boundary, the mid-ocean ridge, and the underwater volcanic activity found along the length of the Atlantic Ocean. A second type of divergence can occur with the spreading of continental plates. continental divergence shares many of the same features as oceanic divergence. As continental crust is pulled apart, superheated material from the mantle causes some parts of the crust to thrust upwards, while others collapse into basin regions, also known as rift valleys. The resultant formation is known as a fault block mountain range. If continental spread continues long enough at divergent boundaries, the opening basin will eventually fill with water and become a new ocean. An example of continental divergence is occurring today between the Arabian and African tectonic plates. Divergence at this boundary has resulted in the formation of the Red Sea. As divergence continues, the Red Sea will continue to grow in size. Convergence is a process that results when two adjacent tectonic plates are situated atop convection currents that pull the plates into one another. When two plates comprised of oceanic crust collide, the denser and usually older of the plates will be pulled underneath the other, less dense plate. The resulting geologic formation is known as a subduction zone. Deep ocean trenches, such as the famed Marianas Trench, are formed at these subduction zones. Moreover, tectonic activity is common along subduction zones and can result in underwater volcanoes and tsunami-inducing earthquakes. If subduction activity is prolonged for millions of years, volcanoes often rise out of the ocean to form island chains in the shape of an arc. An example of two oceanic plates converging can be found between the Pacific and North American tectonic plates. The older and slightly denser Pacific plate has subducted beneath the North American plate, resulting in the formation of the Aleutian Island chain. The Aleutian Islands formed from a volcanic island arc and comprise the southwestern tip of Alaska. A subduction zone can also be formed when oceanic and continental plates converge. In this case, the denser oceanic crust is pulled or subducted beneath the less dense continental crust. Again, a trench is formed along the convergent boundary. Earthquakes and volcanoes are also common. However, the volcanoes often form inland as they rise through the crust of the continental plate. Oceanic-continental convergence is occurring today between the Nazca Oceanic Plate and the South American Continental Plate. The Andes Mountain Range of South America formed as a result of subduction along the convergent boundary between the Nazca and South American plates. Volcanoes from this range form part of what has come to be known as the Ring of Fire, which nearly encircles the entirety of the Pacific Ocean. A third and final form of convergent boundary forms with the collision of two continental plates. In the case of continental-continental plate convergence, subduction is rare, and so are the volcanoes that usually form as a result. Rather, the two plates tend to buckle and to form under the stress of convergence. As the two continental plates converge, rocks within the plates are thrust upwards and over the course of millions of years form folded mountains. Violent earthquakes are common at continental convergent boundaries and release staggering amounts of energy as the two continental plates grind against, over, and under one another. The convergence of two continental tectonic plates is occurring on our planet today between the Indian and Eurasian plates. One result of this convergence has been the formation of the most stunning mountain range in the world, the Himalayas. In the case of the Himalayas, the Indian and Eurasian tectonic plates have been converging for the last several million years. Evidence suggests that they continue to do so, as the height of the Himalayan mountains grows every year. The last type of plate boundary that we will explore is known as a transform boundary. A transform boundary occurs when two tectonic plates move parallel to each other in opposite directions. Neither mountains nor volcanoes form along transform boundaries, but earthquakes are very common. Earthquakes occur due to the stress that builds up along the fault in a transform boundary. When the stress becomes too great, the plates shift and the friction caused by the shift releases energy in the form of an earthquake. The Pacific and North American tectonic plates have created a transform boundary in Southern California. The San Andreas Fault is a transform boundary between both of these massive tectonic plates. On occasion, the plates release built-up energy as they move past one another, and massive earthquakes rock regions along the Californian coast, from San Diego to the Baja Peninsula. As we conclude this lesson on plate tectonics, we'll discuss one final phenomenon known as a hotspot. Hotspots don't occur along plate boundaries, but rather in the middle of tectonic plates. A hotspot forms when a section of the Earth's mantle is particularly hotter than the surrounding mantle. The intense heat produces a mantle plume that rises upward and, in combination with thin or weak tectonic crust, produces volcanoes on the Earth's surface. Although hotspots tend not to move, the tectonic plates above do. Over time, therefore, hotspots can leave a trail of volcanoes, with the youngest and most active sitting atop the hotspot. The Hawaiian island chain is an example of an active hotspot. The Kilauea volcano on the Big Island of Hawaii is the present-day site of a hotspot in the middle of the Pacific tectonic plate. The volcanoes on the older island, Kauai, are no longer active because the island no longer sits above the hotspot. As the Pacific tectonic plate continues to move to the northwest, the Kilauea volcano will also eventually become extinct. Meanwhile, a new island may be born as the hotspot continues its volcanic activity, and thus possibly adding a new member to the Hawaiian island chain many millions of years in the future. So to recap, Earth's crust is composed of tectonic plates that fit together similar to pieces of a jigsaw puzzle. Of materials from which these plates are made, oceanic crust is slightly more dense and not as thick as continental crust. Divergent, convergent, and transform plate boundaries result in a variety of landforms and geologic phenomena. And hotspots produce volcanic activity in the center of tectonic plates, sometimes resulting in volcanic mountain chains. Well, that wraps up our video on plate tectonics. I hope you enjoyed it and look forward to seeing you next time. Until then, ad astra.